So we're going to go ahead and work an example that would be typical of what you're going to see for the homework for section 2.1. Before we jump into this, I want to go into the law of cosines and the law of sines. Let's do a quick review. I'm going to draw a triangle. We've got three vectors. We're going to call them P, Q, and R. We're also going to assign three angles. Opposite of P will be A. Opposite of Q will be B. And opposite of R will be C. For vector notation, we'll put an arrow over P, Q, and R. And let's write down the law of cosines. R squared is equal to P squared plus Q squared minus 2PQ cosine C. Onto the law of sines. The sine of angle A over the magnitude of P is equal to the sine of angle B over the magnitude of Q, and that's also equal to the sine of C over the magnitude of R. Let's go ahead and work an example now that we've got those tools. I was driving today and I saw a telephone pole. The telephone pole had two wires. They're called guy wires, G-U-Y. These guy wires counterbalance the tension of a power line that may be at the top of the power pole. So let's say in 2 dimensions, you've got a power line and it's going to have tension in it. So it's going to tend to pull the pole in that direction. This particular telephone pole had two guy wires. Now those two guy wires were connected to the same point on the telephone pole. And because of that, we call these concurrent forces. And these two guy wires were going to tend to pull on the telephone pole. And you know from physics that those two guy wires are going to have X and Y components to them. I've drawn a Cartesian coordinate system. That's something that we always want to do. And it is the X component that counterbalances the tension of that power line that is tending to pull in the negative X direction here. So what we want to do in this particular problem is we want to find the resultant force of those two guy wires. For now, we're not going to worry about the power line that I have said is pulling off in the negative X direction. So I'm actually going to erase that so we don't get confused by that. That yellow arrow is just a pointer, so I'm going to get rid of that. I'm going to label the two guy wires. I'm going to call this guy P, this guy Q. Now, this is pretty close to a free body diagram, but just for completeness, I'm going to go ahead and draw a free body diagram. And it's not actually going to show all the forces. We're just finding a resultant force for the tension in lines P and Q. But if I were going to draw a free body diagram, again, it's going to look very similar. I'm not going to show the forces at the bottom of the power pole because we're not being asked to solve for unknown forces in an equilibrium type problem, which comes later. So for now, I'm going to leave the bottom of the power pole as is. Yes, there would be forces down there from the ground. We call those reactions. But for now, I'm not going to do anything with that. I'm going to draw the vectors P and Q. And I didn't get out of the car and measure any of the angles, but let's just make some up. (15 and 20 degrees). And let's just say that the force or magnitude, that is the tension in line P, is equal to 520 pounds. And let's say that the tension in Q is equal to 700 pounds. They are both pulling. Cables can only do that. They can only pull. Cables cannot push. And so it's easy to know what the direction of the force is. Remember, on a free body diagram, we're always showing the direction of the forces as they pull on the body. In this case, it is the power pole. So it is not the reaction of the power pole pulling back on the cables. The power pole is actually the body. So we're showing the forces that act on it. And those two power lines pull on that body. So we have shown them pulling away. So we said that the whole point of this is to find the resultant force that would be equivalent to the individual forces caused by P and Q. I like to use the triangle rule. The other option would be to do the parallelogram law. To solve for that, you're typically drawing on a piece of graph paper. You're drawing P and Q proportional to their magnitudes. So you may draw them at 5.2 inches and 7 inches at the appropriate angles. When you're doing the parallelogram law, you draw that different. You do what we call tip to tip drawing of the vectors, and then you actually measure the resultant force. Once you've done that using your ruler, not very practical, I guess a good exercise, but I don't think it's necessary to do here. So I'm actually going to be using the triangle rule instead of the parallelogram law. And in the triangle rule, just to remind you, we draw our vectors in a tip to tail arrangement. What does that mean? I'm going to start off by drawing the force P. I'm going to draw a reference vertical line. We know that P comes off at a 15-degree angle. And then when we say tip to tail, from there I'm going to draw Q. The angle is exaggerated, but it'll work. And we know that Q is drawn at an angle of 20 degrees from P. So that would be a 35-degree angle from vertical. Once we've done that, what is the resultant? The resultant is the length from the beginning, the very first tip, or pardon me, that's the tail, all the way to the tip of Q, and that is our resultant vector R. A little bit of geometry. We need to know what this angle is right here. So how do we do that? Well, a little bit of a tip. I'm going to extend my vertical line And I know that if I have 35 here, I know that I have to have a 145-degree angle here between these two, 145 and 35, of course, adding to 180. And then if I have a 15-degree angle here, then I know that the opposite angle on this side has to be 15 degrees also, for a total of 160 degrees. I, of course, know that, again, to reiterate, the force of P is equal to 520. The force of Q is 700. Just double check those. Yes. Okay, now what we need to solve for next is, well, if you didn't know what to do, let's go analyze and see what we do know. Okay, so we know what the value of P is. We know what the value of Q is. We know one angle inside the triangle. We don't know R. But what we're going to do is, if we write out the law of cosines, R squared is equal to P squared plus Q squared minus 2PQ cosine B, pardon me, cosine C. We know that if we look at that, we've only got one unknown. It is R squared. Now you might be saying, well, do we know C? We do. C is the angle opposite of R. In this case, it's the 160-degree angle. Just for clarity, let's go ahead and label A. Angle A is the opposite of P. And angle B is opposite of Q. So let's go ahead and solve for R squared, or R. R squared is equal to 520 squared plus 700 squared minus 2 times 520 times 700 cosine 160. And if you punch that out on your calculator, R is equal to 1201. There's more significant figures. You can leave those in your calculator as you do further calculations. But one of the things that we wanted to find was the resultant. We're going to do 4 significant figures for anything that starts with a 1. So for an answer, we can go ahead and state the resultant as 1201. We'd leave it in the calculator as more digits if we're going to continue on, which we are, because we're going to find the direction of that resultant R as well. So let's continue on and do that. We're going to use the law of sines to help us with that. I'm going to point out that sine of the angle B over the magnitude of Q is equal to the sine of angle C over the resultant magnitude R. And if you look at what we have here, we know what sine of C is. We know what R is now. We know what Q is. And we can find angle B. What good does that do us? Well, if we know angle B, then we can add it to 15 and know what the direction of R is with respect to vertical. So let's go ahead and do that. Sine of B over Q, which is 700, is equal to sine of C, which is 160, over R. We calculated at 1201. Of course, you can have more sig figs in your calculator and just do the math there, and you'll find that the angle B is equal to 11 point, and check my calculator here, 49 degrees. Again, starts with a 1. We're going to leave it at 4 sig figs. If it doesn't start with a 1, we'll leave it at 3. So we've got a resultant force, R. That's what's pulling on that telephone pole. It's at an angle of 11.49. We're going to add the 15 to that. Adding 15 to give us a 26.49 or 26.5. And resultant of 1,201 pounds. And there you go. Recap. What did we do? We took two coplanar forces acting on a telephone pole. They are concurrent because they act at the same point. We knew the magnitude and direction of each of those. We wanted to find the resultant force, so the same equivalent force. We wanted to find the magnitude and the direction of that force. And that's what we've done.